Hi, this is Algebra 1, Topic 1, Solving Equations and Inequalities. In this topic, we'll think about the topic essential question, what general strategies can you use to solve simple equations and inequalities? If you look at topic overview, you can see that there are 7 lessons total. We'll start with operations on real numbers, and then look at solving linear equations with a variable on both sides, and learn what literal equations and formulas are, and continue with solving inequalities in one variable and compound inequalities, and we'll end with absolute value equations and inequalities. So these are some topic vocabularies: compound inequality, element of a set, formula, identity, literal equation, set, and subset. So whenever you see these topic vocabulary explained throughout the topic, please make sure you note them in your math notebook or put in a graphing organizer, would be even better, so that you can see them all at the same time. All right, let's start with lesson 1, operations on real numbers. In this lesson, we'll be able to reason about operations on real numbers. We'll see vocabularies, element of a set, and subset in this lesson. Let's start with critique and explain. Cindy and Victor are playing a math game. The winner just must get 3 in a row of the same type of a real number and justify how the numbers are alike. Cindy says she won because she was able to get 3 rational numbers on a diagonal. Victor said he won with 3 positive numbers in a column. Okay, so we can see that Cindy is probably representing which color? 3 rational numbers on a diagonal. Diagonal is represented as the red one. So that's Cindy. This is Cindy. And Victor is arguing that he won because he got 3 positive numbers in a column. Okay, so what do you notice about the numbers shown on the game cards? Is Cindy right or is Victor right? If we look at Cindy's cards, we have 1.3, 2/5, and 27. It includes decimal, a fraction, and a whole number, right? So, are these all part of rational numbers? Yeah, if they could be written as fractions, they're rational numbers. Is rational number a real number? Yes. These are all rational numbers are real numbers. Victor's cards, if you look at Victor's cards, 1.3, square root 10, and pi. And he's saying he got 3 positive numbers in a column. Well, they're all positive, right? Yeah. The numbers include decimals, square roots, and irrational number. Pi is an irrational number because if you put pi into a decimal, it's non-repeating and it's non-terminating. So you cannot rewrite pi as a fraction. Pi doesn't have a fraction form. So if you don't have a fraction form, then that is an irrational number by its definition. Is irrational number also included in a real number? Yeah. So irrational numbers, rational numbers are all included in real numbers. And they're all positive numbers. Positive numbers are real numbers. So, is Victor correct? Sure, Victor's numbers are also all real numbers. 2 are irrational, 1 is rational. Cindy's numbers are all rational numbers, 1 number, decimal, fraction, and a whole number. So, if the game was to find all 3 rational numbers, Cindy would win. But the game is about getting all real numbers in a row. So they can both say they won with different reasons. So that explains part A here. Let's write part A. So yes, can both players say they won for different reasons? Yes. Why? Cindy used a subset of real numbers called the rational numbers, while Victor chose positive numbers as a type of real number. He did not attach any special meaning to the word type. So they're both correct. Part B, reason. Can you make other groups using the numbers shown that are all the same kind of real number? In how many ways can you do this? So the same kind, what does it mean to have the same kind? You can have rational numbers or irrational numbers, or if you have negative numbers or positive numbers, they could be the same kind, or integers, whole numbers. So we know these group of numbers that is a subset of real numbers. So what is a subset? Subset is a set of numbers that is included, all the numbers in that subset is also included in another bigger set. Okay, so part B, we can say yes, you could group the numbers as rational and irrational. Other examples include positive and negative numbers, numbers written with a radicand, and those without. Radicand is where you have the square roots and the numbers. Those without, numbers whose square is an integer, and those that do not have integers as squares. So this is part B. Whoops. So sorry. Okay, so let's start with asking the essential question. How can you classify the results of operations on real numbers? Let's start with example 1. Understand sets and subsets. In the set of numbers from 1 to 10, which elements are in both the subset of even numbers and the subset of multiples of 5? So it includes even numbers, and it also has to be multiples of 5. So by definition, a set is a collection of objects such as numbers. Okay, it's a collection of things. An element of a set is an object. One object that is in the set. Write a set by listing the elements in close and curly braces. So if you look at this set A is the name of the set, and you can put all the elements of the set by using commas in between. And you can enclose the set with curly braces like these. This is how you write a set. Okay, set B is a subset of a set if each element of B is also an element of A. So all the element of B has to be in the element of A in order for B to be a subset of A. So B, 2, 4, 6, 8, and 10 are all included in the set A, right? So B is a subset of A. C is also a subset of A, but includes different numbers than B does. So 5 and 10 would be a subset of A. And elements of A that are even would be described with this subset B. Elements of A that are multiples of 5 would be C. And the element that is in both the subset of B and C would be 10. So the number 10 is the only number that is an element of both subsets. So using sets and subsets, you need to know how to describe which element would fall into the category that we need. So now it's your turn. Try answering this question. Which numbers in set A are elements in both the subset of odd numbers and the subset of multiples of 3? So if you can do it by yourself, come back when you're ready for answers. Okay, are you ready? So how can you write a subset of B and C with a different elements? Or if B and C are confusing you because we already used it on top, we can do D and E. Okay, so the subset of D would have odd numbers from A. Okay, so all odd numbers would be 1, 3, 5, 7, and 9 from A. And E would represent the subset of multiples of 3 from set A, right? So then you would have 3, 6, and 9. What are numbers that are included in both the subset D and E? You can see that 3 is both in D and E. 9 is also in both subsets. So in this case, you have 2 answers, and that's okay. 3 and 9 would be your answer. So check your answer. If you got it correct, good job. Let's look at example 2. Compare and order real numbers. Let's apply what we just learned. Jim is playing a math game where he needs to put a set of 3 cards in numerical order. His cards show 40 over 11, square root 324 over 36, and square root 10. Order the cards from least to greatest. So this should have been what you already learned in the previous years. You should know how to change fractions into decimals, irrational numbers into a decimal, or simplifying square roots as well. What is a square root? Square root is related to powers and multiplication. So 2 times 2, for example, would be 4, right? You can write that as 2 to the power of 2 because we're multiplying 2 times. And you can say that the square root of the answer of the power, right, square root 4 would be 2 because square root asks you how many times a number should be multiplied. So square root says what number has to multiply itself twice to get the number inside a square root. Okay, so if you have a fraction inside a square root, you can simplify the fraction, and you can also apply the square root in the numerator and the denominator. So in this case, you know that 40 over 11, if you divide it literally, 40 divided by 11, you should get 3.6363 repeated. But for the square root, you can change this into a separate number. Square root 324 and square root 36. And how do you simplify square roots? How do you know what numbers would multiply itself twice to get 324? Right? You know that 10 times 10 is 100. So comparing your numbers, 100 and 324, 324 is greater than 100. And if you think about it, you can keep guessing and checking until you get to a number that is exactly multiplies itself to 324, or get a close number that are in between. Okay, so in this case, you can guess and check, or another way is to factor it out. 324, if you factor it out, if you divide 324 by 2, you get 162. And divide it until you cannot divide. So divide that by 2 again, you get 81. Divide it by 3, and you get 27. Divided by 3, you get 9. Divided by 3, you get 3. So this means if you multiply 2 times 2 times 3 times 3 times 3 times 3, you get a 324. And if you write that into a square root, 2 times 2 times 3 times 3 times 3 times and 3, you can say that square root 2 times 2, which is 4, is 2. And you can say that square root of 9, which is 3 times 3, is 3, because 3 times 3 is 9, right? And in the same way, you can say that you can separate these numbers. And so, ultimately, this is equal to 2 times 3 times 3. And that number is 18. So this simplifies into 18 over 6, because 6 times 6 is 36. You can use the same method if you are not familiar with square roots. Okay? So that is 18 by 6. If you simplify that again, you get a 3. And this square root 10, you don't have an exact number for that. You're going to get something between 3 and 4, because 3 times 3 is 9, and 4 times 4 is 16. So 10 is between 9 and 16, which is a whole number. So you know your answer is going to be between 3 and 4. Okay, so you can estimate it to 3.2 and line them up in a number line like that. So from least to greatest, the order of the cards will be square root 324 over 36, square root 10, and 40 over 11. So let's try number 2. See if you can do it by yourself. Order each set of cards from least to greatest. Okay, are you ready to check for answers? All right, if you change them into decimals, what would come first? 6 over 25 is 0.24. And 9 over 6 is 0.11, but if you square root that, you get 0.037. 7 repeated. Okay, and 0.25 is 0.25. So listing from least to greatest, you should get 6 over 25, and then 0.25, and then square root of 1 over 9. Okay, in the same way, part B, you should get square root of 121 over 25. And 0, and then square root of 5. And then you should get 2.25. Okay, check your answers if you got all of them correctly. Great job. Example 3. Operations with rational numbers. Part A. Is the sum of two rational numbers always a rational number? You can try several different cases of adding two rational numbers to see if it always works. So if you look at the first example here, you get 1 over 2 plus 1 over 3. That's going to be 5 over 6. And 7 over 8 plus 3 over 4 is 13 over 8, and that's a rational number. 11 over 5 plus 1 over 6 is 71 over 30. That's also a rational number. In each case, with a random example, the sum is also rational. But you literally can't try every pair of rational numbers because there are infinitely many rational numbers, right? So it's just not possible. So how do you know whether it's true for all rational numbers? You can use variables to represent all the numbers of a set. So you can use A, B, C, and D as integers. So that B is not 0 and D is not 0, because if there is 0, this fraction doesn't make sense. There cannot be a fraction with a denominator of 0 by definition. Okay? So using this assumption, we're going to write an equation that says A over B plus C over D to represent a sum of rational number, with any number of integer. Okay? So this could work with all rational numbers. So if we keep solving it using the variables, we can have A times D over BD would be where we can rationalize our denominator. We can match our denominator, right? So then, because we need to multiply B times D in order to get the same denominator for the variables. If we multiply this fraction by D, we cannot just change the fraction. So D over D is like multiplying by 1. So if we multiply A by D and B by D, then we're not changing the fraction. So we can do this. AD over BD plus BC over BD would be equivalent to A over B plus C over D. And then we can add AD plus BC. And we know that both B or D would not be 0. So this fraction makes sense because any integer plus an integer would be another integer. Okay? So yes, now we can say that the sum is rational because AD plus BC and BD are integers, and BD would not be 0. Part B. Is the product of two rational numbers always a rational number? You can use the same strategy as in part A, using variables, so that A, B, C, D are any integer. They could represent all integers. Okay? But B and D cannot be 0. So they have a restriction. And if you multiply them, you get A times C equals B times D. And you know that B and D are not 0, so B times D could never be 0. So this fraction makes sense. And so it's always going to be a rational number. So you can say that since AC and BD are integers and BD is not equal to 0, we can say that the product is rational. So why is it necessary to show that the sum and the product of a rational number and an irrational number is always irrational? By contradiction. There's no way to write a direct proof because there's not a general form where irrational numbers can be represented. So using rational numbers, it's actually easy. Let's look at try number 3. Is the quotient of two rational numbers always a rational number? So using the same method, we can write a quotient statement and then prove or not prove that it's a rational number. See if you can do it by yourself and come back when you're ready for an answer. Okay, are you ready? Yeah, so how do you write a quotient equation with these variables? So you can do the same thing. A over B could represent one rational number where B is not equal to 0. And say that A over B divided by C over D would be our equation. And we can say that A, B, C, and D are integers. With B not equal to 0 and D not equal to 0. Okay, has the same condition. And now we need to solve it. You can change this equation into a multiplication equation, right? Change this into a multiplication by using the reciprocal. And you can say that A times D over BC would be the quotient of this. D and B are not 0, right? If C is a 0, then it cannot be a rational number. So you can change this into C also not equal to 0, not being equal to 0. Okay, and then you can make it true. So A, B, C, and D are integers. Any integers with B and C and D not being a 0. Okay, so if A is a 0, then you get an answer of 0, and that's still a rational number, so that's fine. But we do need a little bit more of a restriction here. Okay, let's look at example for operations with rational and irrational numbers. Part A. Is the sum of a rational number and an irrational number rational or irrational? What about a rational number and an irrational number here? It's the sum of one rational and be a rational number. So we can say A over B plus C could equal to P over Q, where we assume that the answer is rational, right? And then if it works, then it works. If it doesn't, we can contradict and say it doesn't work. So in the rational numbers above, A, B, P, and Q are integers, and C is the only one that is representing the irrational number. Okay, so this means when we solve for C, C is equal to PB minus AQ if we solve for the equation. I think since they skipped the steps, for just in case you don't know how to do that, let me write it down. So if you subtract A over B in both sides, then A over B minus A over B is 0. So you get a C is equal to P over Q minus A over B. And in order to subtract them, you multiply the denominators and make PB over QB minus AQ over BQ, right? And then you can mix the numbers. You can use commutative property to reorder QB as BQ. Okay, so you can say C is equal to PB minus AQ over BQ. And you know that B and Q cannot be 0. And this means that PB minus AQ is an integer because A and P are A, B, P, and Q are all integers where B and Q are not zeros, right? So therefore, this is a rational number. It has to be a rational number. And C has to be an irrational number. So if C is equal to something that represents a rational number, it doesn't make sense. So that means our assumption here is incorrect. So rational number plus irrational number cannot be a rational number. So yeah, our mistake was to assume that we could write a sum A over B plus C in the form of P over Q. So the sum of rational number and an irrational number is always an irrational number by contradiction. Okay, so why is it necessary to show that the sum and the product of a rational number and an irrational number is always irrational by contradiction? So again, there's no way to write a direct proof. You can't say rational number plus irrational number and you can't solve for it because you don't know how to add them if C is irrational and A over B is rational, right? Like, you're stuck. So you have to assume first and contradict. Okay, so part B is about rational number, the product of a rational number and an irrational number. In the same way, we're going to assume that the product is rational and solve for the irrational number. And BP over AQ is a rational number, so the assumption that the product would be a rational number is incorrect. So the product of a rational number and irrational number is always irrational unless the rational number in the product is 0. So how does the product change if the factors are 0 and an irrational number? The product must be rational since the product will be 0. If you get a 0, 0 is part of a rational number. So this only works when the product is not 0. All right, so let's look at try number 4. Is the difference of a rational number and an irrational number always irrational? See if you can continue with this logic and use use the assumption to contradict your assumption and prove it wrong. So see if you can explain this by yourself. Come back when you're ready for answers. Okay, are you ready? So in the same way, you can assume that a over b, rational number, minus irrational number c, you can assume that a over b rational number minus a c that represents irrational would be rational, p over q. And see if it works. And if it contradicts, then our assumption might be wrong. And we can say that it's always going to be an irrational number, right? So then you solve for c. And if you add c on both sides and subtract p over q on both sides, you get a over b minus p over q, which is equal to c. And you know that this is going to be aq minus bp over bq. And this is a rational number because all a, b, p, and q are rational numbers or integers where b and q are not zeros. So because b and q are not zeros, this all of this makes sense with all the integers, right? It's going to be a rational number. So c cannot be an irrational a rational number because c has to be an irrational number. So this contradicts itself, which means it always has to be the difference of a rational number and an irrational number always has to be irrational. Okay, so we're using the same method. So we can say yes. Since m cannot, since c cannot be written as the ratio of two integers, a minus bm also cannot be written as the ratio of two integers. All right, that was a great start of the topic. Let's summarize our lesson 1, operations on real numbers. You already know how to do adding, subtracting, multiplying, and dividing. This lesson was all about trying to understand what it really means to have a set and subsets of real numbers and how they work when they have different operations with different sets. So the sum of two rational numbers is always rational, is what we observed. The product of two rational numbers is always rational as well. But the sum of a rational number and an irrational number is always irrational. And the product of non-zero rational number and an irrational number is always irrational. So these are the four major rules that we discovered throughout this lesson. And we already know how to prove them. So now if you see these examples like sums, products, sums and products, where you have rational plus rational, rational times rational, you know you're going to get a rational number. Irrational plus rational and irrational times rational, you know you're going to get an irrational number. Okay? So even without knowing what the numbers exactly are, you should know rational times rational is rational. But rational times irrational is irrational. Okay? Alright, that was lesson 1, operations in real numbers. If you have any other questions, please feel free to ask Ms. Kang in class. Otherwise, we'll continue with lesson 2, solving linear equations, in the next video. Thanks for watching, guys. Bye!